Good morning everyone. Now let's see next theorem on linear independence. Linear independence. Okay. So statement of theorem is let V be a vector space over F if V1, V2, Vn belongs to V where V1 is not equal to 0, then either they are linearly independent or some Vk is a linear combination of the preceding ones V1 up to Vk minus 1. Okay. Proof is very easy. If V1, V2, Vn are linearly independent, then we have nothing to prove. Yes. Let V1 up to Vn belongs to V. Yes. Then there are two cases arises. Yes, two cases arise. Okay. So first one is V1 to Vn are linearly independent, and second case is V1 to Vn are linearly dependent. For first case, for the case 1, there is nothing to prove. Yes, there is nothing to prove. Hence, assume case second. Okay. So for that, for case second, consider alpha 1 V1 plus alpha n Vn is equal to 0. We have to prove case second. Call this as equation 1. Okay, call this as equation 1, where we always know what alpha, all scalars belongs to field F and are not all 0. All alpha are not 0, and they have given what in statement of theorem they have given V1 is not equal to 0. We have to assume this case V1 is not equal to 0 and not alpha are 0. Okay. Since not all alpha I are 0, yes, there exists the largest integer, suppose k greater than 1, such that alpha k not equal to 0. Yes, because we are taking condition that not all alpha are 0. Okay, so take alpha k not equal to 0. This implies I greater than k. Yes, where alpha I is equal to 0, that is alpha k plus 1, alpha k plus 2 up to alpha n is equal to 0. Okay, this implies what? So we can write equation 1. So what is equation 1? Alpha 1 V1 plus alpha 2 V2 plus alpha k Vk plus alpha k plus 1 Vk plus 1 plus alpha n Vn is equal to 0. Yes. So what we have assumed that? We assume that alpha k plus 1, this part is 0. Yes, this part is 0. So we can write this equation 2 as rewrite equation 2. We get alpha 1 v1 plus alpha 2 v2 plus alpha k vk is equal to 0. Yes. By equation 2, by equation, or we can say by by equation 2. Okay, so what we have assumed? We have assumed that, or we can write this equation as alpha k vk is equal to c. Take all these terms to RHS, so you will get minus alpha 1 v1 minus alpha 2 v2 minus alpha 3 v3 up to minus alpha k minus 1 v k minus 1. Understood? Okay. So, and we assume that what, as alpha k is not equal to 0, means we can define inverse of alpha k. Yes, 1 by k is defined. Yes, because in denominator there is no 0 term. Okay, so this implies what, alpha k inverse exists. Okay, then multiplying the above identity by alpha k inverse, we get alpha k inverse. Yes, alpha k inverse. So multiply this equation by alpha k inverse. Call this as equation 3. Multiply the above identity, or multiply the above equation 3. Okay, by alpha k inverse. So you will get alpha k inverse alpha k vk is equal to alpha k inverse in bracket minus alpha 1 v1 minus alpha 2 v2, yes, minus alpha 3 v3 and minus alpha k minus 1 v k minus 1. Okay, multiply both side by alpha k inverse. So you will get alpha k inverse alpha k vk, okay, is equal to minus alpha k inverse, take scalars in one bracket and outside of that bracket write vectors. Okay, minus alpha k inverse alpha k minus 1 v k minus 1. So this implies v1 is equal to minus alpha k inverse alpha k, yes, so v1 is equal to alpha k inverse alpha k inverse alpha 1 v1 minus alpha k inverse alpha k minus 1. Yes, so since alpha k inverse alpha k is equal to identity element, yes, identity element. See here, alpha k inverse and alpha k, minus 1 plus 1 becomes 0. So here only there is term v k, yes. So hence vk, hence vk is a linear combination of v1 to vk minus 1, and hence we have proved that vk is a linear combination of v1 to vk minus 1. Thank you.